So let's look at some examples from 8.3. So if we start out by looking at complex numbers, let's look at plotting on the complex plane. So the horizontal direction, that's the real direction. The vertical direction, that is the imaginary direction, or we sometimes refer to it as the y-I direction. So if we have a complex number, let's say 3 plus 4i, to plot that, we go 3 in the real direction and 4 in the imaginary direction. So over 3, up 4. So keep in mind this is not I hat as in a vector, but this is just a complex number, a real part plus or minus an imaginary part. So 3, 4, I will be located there. If we wanted to plot 2 minus 7i, then we would go 2 in the real direction, so over 2, and down 7 in the imaginary direction. So we would have a point there. If we needed the point -4 plus 2i, we go to the left 4, that's in the real direction, 2 in the imaginary direction. If we wanted to plot the real number 3, that has 0 imaginary parts, so we would just go over 3. So another thing we have to do is to find the absolute value of a complex number. So let's graph one. Let's graph 3 plus 4i. So that point is the location of that complex number. The absolute value of 3 plus 4i is like finding any absolute value. What absolute value really means is the distance that that particular number is from the origin. If we take the absolute value of the number 5, we get 5 because that number is 5 units from 0. If we take the absolute value of -3, we get 3 because that number is 3 units from 0. If we have a complex number, it's a little bit more complicated because to get to 0, we would go in a straight line. So it's a combination of how far we've gone in both the real and the imaginary direction, but it's not just 3 plus 4 is 7. It's basically if we have a triangle that is 3 in the real direction, 4 in the imaginary direction, what is the hypotenuse? So that distance is the absolute value of 3 plus 4i. That's how far this point is from the origin. So to get that distance squared is the real part squared plus the imaginary part squared. So 9 plus 16. So take the square root of that. So the absolute value of 3 plus 4i is 5. So we have to make sure we use the formula. So sometimes the formula is written like this. If we want the absolute value of a complex number, it's the square root because we had to get the square root, take the square root to get the hypotenuse. It's the real part squared, so that's a squared, plus the amount of the imaginary part. Notice we didn't square 4i, we just squared 4. So the coefficient of I squared, and those are added together. So basically the Pythagorean theorem, where A is the real distance, B is the imaginary distance, and we're looking for that hypotenuse. So another thing that we might need to know is that angle, the direction of that complex number. So if we want to find theta, we have 4, the imaginary part is opposite of theta, 3, the real part is adjacent, so opposite over adjacent is tangent. So generically, tangent theta is the quantity of the imaginary part over the quantity of the real part. So if we do inverse tangent of 4/3, do inverse tangent of 53.1 degrees. And we just have to make sure that that is pointing in the right direction. And yes, from here, that direction is about 53.1 degrees. So we've got the magnitude, or the absolute value of that complex number, and the direction of that complex number. So these are the formulas we're going to use to find that. So another question might be to take 3 plus 4i and convert it to trig notation. So trig notation is z times cosine theta plus I sine theta. And I can't remember if they use z or if they use r, what they use for here. But where that value is the absolute value, and let's just do it like this, the absolute value of our complex number, and these angles, which are going to be the same angles, that's the direction. So 3 plus 4i can be converted into trig notation as 5 times cosine 53.1 degrees plus I sine 53.1 degrees. And if you watched the lecture video, then you may have seen the derivation of why that's the case. So let's check. How would we check to see if that's true? So we want to distribute this out. We would have 5 times cosine 53.1 degrees plus I times 5 sine 53.1 degrees. And we want to see, does that make 3 plus 4i? So if we do 5 times cosine of 53.1, we get 3.002, which is not exactly 3, but keep in mind this angle was not exactly 53.1. That was rounded a little bit. But for all intent and purposes, that is 3. When we do 5 times sine of 53.1, for all intent and purposes, we get 4, and that's the coefficient of I. So yes, that works. So if we call that Z or R cosine is the horizontal part. That's R cosine. R sine, that's the vertical part. They just factor the R out front and leave the cosine and I sine on the inside. So this is how we go back and forth between standard notation and trig notation for a complex number. Standard notation looks simpler, and there are times where standard notation is simpler to use, is better to use, but there are also instances where complex notation is better to use. So the next thing we want to do is multiply complex numbers together that are in trig notation. So if we have 2 cosine 20 degrees plus I sine 20 degrees, and we multiply that times 5 cosine 10 degrees plus I sine 10 degrees, then the formula that we use to multiply those together is that we multiply the radii together and we add the angles. So this angle plus that angle. So 20 plus 10 would be 30. And then the same angle for sine. 20 plus 10 is 30. So if we multiply that complex number times that complex number, we get 2 times 5, so 10. So the radius, the absolute value, or you can call that the magnitude of it, the magnitude is greater, and then it's also been rotated. If one of them is in a direction of 20 degrees and the other is in a direction of 10 degrees, then when we multiply them together, we've actually rotated 30 degrees. So just the sum of those angles. So let's do this one. They give us 12 plus 12i times 2 minus 2i. They ask us to convert each of these into trig notation and then multiply them together, and then they want the answer in standard notation. Now, really, if we were multiplying these two together in standard, or multiplying these together and they're already in standard notation, the easiest thing to do would be to distribute and combine like terms. That would actually be much faster. But for practice, they want us to make these conversions. And while this is faster this way, one thing we may see in the future is that if we needed to take something like this and multiply it times itself, but not just times itself once, let's say times itself 7 times, if we were doing this times itself once, so basically squaring it, it'll be easier just to FOIL it out. But if I have to write this factor 7 times and distribute all of that together, that would take quite a bit. So some things that we can gather when multiplying it in trig notation may make this particular operation easier. So if we were just to quickly think about 12 plus 12i, that's to the right 12 up 12. If we've gone over and up the same amount, then what direction is that? If this is over 12 and up 12, we could do tangent theta is 12 over 12, which is 1, and then do inverse tangent of 1. Nothing wrong with that. But that's 45 degrees. If you go over and up the same amount, then your angle is 45 degrees. So for this one, the angle part is 45. We just need to put the radius out front, or the magnitude, the absolute value. So the distance for that one is the square root of the real part squared plus the imaginary part squared. So that's 144, and that's 144. We could add those together and get 288, or let's call that 2 times 144. And the reason for doing that is if we have a product, we can take the square root of each of those. And we know that the square root of 144 is 12, and 2 is not a perfect square. So that's just 12 square roots of 2. If you think about if this were 1 and that were 1, that would be a 45, 45, 90 triangle, 1, 1, and square root of 2. Well, we've just scaled that up by 12. So if we multiply this by 12, we multiply that by 12. So hence 12 square roots of 2. Now if we look at 2 minus 2i, that's to the right and down, to the right 2, down 2. Well, that's also going to be 45, but that's in a direction of negative 45. So the angle, we could call it negative 45, or we could call it 315, either one. And then we need to get the magnitude for it. Well, we'll use a shortcut. Just like we said, that top triangle is 1, 1 square root of 2, 1, 1 square root of 2. So this triangle has been doubled in size. So that would come out to be 2 square roots of 2. If you don't get that, then you could just say that the hypotenuse is the real part squared plus the imaginary part squared. That's 4. Negative 2 squared is 4. So that's 8, or 4 times 2. The square root of 4 is 2. Square root of 2. All right. So that puts each of those complex numbers into trig form. So now to multiply them together, we multiply them. And what do we do with the angles? We add them. So 45 degrees plus negative 45 degrees. 45 degrees plus negative 45 degrees, which of course that is 0. So instead of writing it out again here, that's 0 degrees. So remember, these angles are the same. So when we combine them, if we're at 45 degrees and then we rotate a negative 45, we get to 0. So we're just adding our angles together. Now we need to multiply these together. So 12 times 2 is 24. If we multiply root 2 times root 2, root 2 times root 2 is root 4, which is 2. So that gives us 48 out front. And cosine of 0 degrees, sine of 0 degrees. So that's our answer in trig notation. Now we just need our answer in standard form. Well, if we're in a direction of 0 degrees, if we're in this direction, and we go out 48 units, then our real part is 48. If we're not up or down any, our imaginary part is 0. So that's our number. We didn't even have to multiply that out. If we did 48 times cosine of 0, we would got 48 for the first part. If we would have done 48 times sine 0, that gives us the coefficient of I. Well, 48 times sine of 0 is 0. So whether we distribute that and multiply it out, or whether we just recognize if we're in this direction, 0 degrees, so that's straight to the right. If we're straight to the right, we're not up any and we're not down any. So our imaginary part would have to be 0. If we're straight to the right, then our horizontal component, which is the real component, is 48. So that's what we're looking for this one. So let's do one where we raise to a power. One thing I just mentioned a second ago, that if we had 12 plus 12i and we needed to raise that to the 7th power, it would take a while to take this and write it out times itself 7 times. But if we have a particular, I'm just going to make one up. If we have a particular complex number that's in trig form, if we're going to square it, then that means multiply it times itself. So if I multiply this times itself, I'm multiplying the radius times itself. And I'm adding the angle to itself, so I'm basically doubling the angle. That would be squaring it. If we had to cube it, then we would multiply the angles together. We'd multiply all the radii together, and we would have the angle 1, 2, 3 times added together. So 3 of those. So that would be cubing it. If we ended up raising it to the 4th power, we would have 4 of those, and we would have this times 4. So it turns out if we want to take a complex number and raise it to a power, then we end up with our radius. Erase this. However many of those that get multiplied together, that's how many times we have our radius multiplied together. So in other words, our radius to that power. And then however many of them we're multiplying together, that's how many times we add the angle to itself, or we have the angle that many times. So if they give us one and say, okay, let's take, let's just make one up. Let's do 2 plus 2i, and let's raise it to the 8th power. So if we're over 2 up to, over 2 up to, that's 45 degrees. You could do tangent theta of 2 over 2 b over a. But when you do that, you're going to get your angle as 45 degrees. So we're going to have cosine 45, sine 45. And then 2, let's start calling this radius, because really that's what it is. So our radius for that complex number is a squared plus b squared. 4 plus 4, that simplifies to 2 square roots of 2. So that's our complex number, not raised to the 8th power. That's just the conversion of 2 plus 2i converted to trig notation. So that and that mean the same thing. So now let's raise it to the 8th power. So to raise this to the 8th power, instead of having to FOIL that out 8 times, we're going to have our radius raised to the 8th, and then we take our angle times 8. 8 times our angle. Sine of 8 times our angle. So let's do the angle part first. 45 times 8, that's just 360 degrees. We could call that 360, or we could call that 0. 0 and 360 are coterminal. So 360 or 0, however you want to write that. And then we just need to do 2 roots of 2 raised to the 8th power. So we're going to have 2 to the 8th power and root 2 to the 8th power. This either way we want to. We could do the 8 on the outside or the 8 on the inside. If we put the 8 on the inside, notice we have 2 to the 8th, and then we're taking the square root of that, which is 16. So we have 2 to the 8th times 16. And 2 to the 8th times 16 is 4,090. And it might be that your calculator will let you done 2 times the square root of 2, and then taking that and raised it to the 8th power, and it giving it to you. So regardless, when we do 2 roots of 2 to the 8th power, we get 4,096. And when we do our angle 8 times, we get an angle of 360 or 0 degrees. So that's our answer. That's raising 2 plus 2i to the 8th power, but that's our answer in trig notation. If we want to convert it to standard notation, our direction is 0, so we're going in this direction, 4,096. We're not up or down any, so that means our imaginary part is none. We're straight to the right, so our real part is 4,096. So anytime you're on one of the axes, you don't have to go through all the formulas to get your real part and imaginary part, or to get your direction and your radius. You can just translate those off. But again, if you don't get that, distribute it. 4,096 times that, type that in your calculator, you'll get 4,096. 4,096 times that, type that in your calculator, you'll get 0. So that's your answer in standard form.